Hello everyone and welcome to another episode of the Hidden Quantum Champions. In today's video we are going to look at another company from the quantum economy space. So without further ado, let's jump right into it. And today we are looking at a company called Photonic Incorporated or Photonic. Here we are on their website. It says distributed quantum computing in silicon. So as we see, we are already right into it. Today we are talking about quantum computing again and silicon. So what does it say? And it's also distributed. So it says here silicon photonics, photonically linked silicon spins and silicon spins. So what do we take from that? We have these two spheres here. Silicon spins as probably in silicon qubits. So silicon as a crystal has a very regular lattice structure. It basically, if you look from all three sides of it on the cube cell, it will look basically the same from all different sides, which is a very regular structure. But it also comes at the disadvantage that it is, let's say, very degenerate. So you have to play a couple of tricks with it. But long story short, doing all of this, you can basically isolate a single spin from the others and can basically use that as a qubit. So kind of separate it from all the 6 degenerate states. So you have basically 2 states in X direction, 2 in Z and 2 in Y. And then if you can separate 2 of them and then separate these 2 again in some way, then you end up with a single silicon spin. And then in addition to that, we also have the silicon photonics here, which is probably using waveguides and so on embedded in silicon chips to connect multiple of these qubits, possibly photonically. However, that one I'm very curious to understand a bit better because as to my knowledge, I think the silicon spins themselves, like the transitions, they are not photonic transitions. But let's jump into it and learn a little bit more about that. So here it says, we are leveraging the memory and computing capability of spins and the connectivity of photonics to build the world's first scalable, fault-tolerant, networked quantum computer. Our approach to quantum computing, and we will see more about that in a second, but let's go down first on this first page here. So our unique qubits, the compute power of spin qubits and the communication capabilities of photons, all in scalable silicon. And I guess we will learn more about that later on. What else do we have here? So there's like this slider with different topics. Photonic Inc. earns a coveted spot in Canadian Defense Challenge to advance quantum networking. There's some more here about top tech leaders to accelerate quantum innovation and growth. Photonic to open quantum R&D facility in the UK, and so on. So this is like the news rider here, the news tab with all the latest news from the company. What else do we have here? So there's something on scalable, distributed, and fault-tolerant. Scalable, it says quantum silicon processes with T centers, enabling fabrication at scale and network expansion. Distributed, qubits capable of communicating by telecom band fiber infrastructure to network modules into distributed quantum computing clusters. And then fault-tolerant, proprietary high connectivity switching architecture enabling efficient, low overhead error correction codes for improved yield and scalability. And what else does it say here? Network quantum computing is the key to global scalability. Some experts down here and a link to their careers page. Okay, so let's learn a little bit more about the technology first. So today we are hopping right away here into the technology. That's what we saw already before. So here it says photonics architecture uniquely networks silicon spin qubits together with photons to overcome the challenge that impede other platforms. The combined solution uses photonically linked silicon qubits to implement a resource-efficient, error-corrected, and truly scalable quantum computing platform. The Photonic silicon spin photon platform establishes a clear path to scalable fault tolerance. So, T-centers in silicon. T-center qubits in silicon leverage the advantages of both spin qubits and telecom photons. Up to 3 nuclear spin qubits, 2 carbon and a hydrogen, can be used for memory and computation in a T-center, and 1 electron spin qubit can be used to do inter-T-center entanglement operations. So here we see, I guess, the unit cell more or less of the crystal, and here is basically the, let's say, hidden fact that I was missing out on. So in fact, we are not actually using the silicon as a qubit here, so the silicon itself, but it is a doped type of silicon, so there's some additional atoms integrated into the silicon crystal. In this case, it says 2 carbon and a hydrogen atom, so these 2 yellow ones here, they are the carbon, and then the green one is the hydrogen atom, and these become these T-centers that can then be used for the computation and also for the memory in this case. So let's see what it says down here. Silicon spins. Spin qubits with silicon have proven to be exceptional quantum memories. They have set performance records for fidelity and lifetimes. The industrial dominance and extensive development of silicon efforts offers such incomparable competitive advantages that historically, if a solution is found using silicon, the silicon solution usually wins. Quick note on that. So all of today's chips, or let's say most of today's chips in compute, they are built using silicon. Silicon is what TSMC is using in the wafers that they are shipping, what Apple chips are built off, what Nvidia chips are built off, what Samsung is using in their chip manufacturing, what Intel is using. So everyone in the industry is using silicon as a standard platform, technology platform for transistors, which are, let's say, the small building blocks of today's processors. Now, there are other types of material. There's like silicon carbide, which is for, I think, high power electronics. There's gallium nitride, which is also for fast chargers and so on. So there are other material classes that are being used in semiconductor industries. However, let's say silicon and the CMOS technology is what is being scaled up the most. So CMOS referring to the processes that are being used to fabricate devices. Now, this statement here basically says, okay, whenever there is some interesting new technology that is incorporating silicon, it is going to be the successful one because of what we have. And there is definitely some truth to that, because today all of the machinery, like the very complex machinery that is being produced to make these transistors for your computers, for your smartphones and so on, this is basically all nanotechnology already. So we have like nanometer sized transistors that are being manufactured in the billions on just a single chip, right? So there's all of this technology already. And if you could use that to make something new with it, to create a new technology, it's probably a promising thing to do, because it would mean that, okay, you can use the same fabs that are producing nowadays chips for smartphones to then create quantum computers. Now, the other thing that we see here is telecom photons, telecommunications band, telecom photons can be flexibly routed with arbitrary connectivity to connect meta qubits both locally and remotely, with low loss and cryogenic compatible waveguides and at room temperature using modern telecommunications infrastructure. Telecom photonic qubits will be the backbone of any highly connected global quantum network and of modular quantum computers. And that refers to, let's say, all the fiber optics that is being already used for fast communication, either within, for example, data centers to connect different data units with each other, but then also to connect data centers with each other, to connect data centers with homes, as in like fiber internet nowadays. So the idea is to use this to use this existing technology infrastructure, as in factories that can produce these very high quality telecommunication fibers and cryogenic compatible waveguides and so on, to basically build a reliable silicon based technology with existing technology stack for quantum now. Each T-center in silicon hosts an electron that can emit telecom photons. So that's what we've seen already before. Then it says horizontally scalable. Each module contains chips with thousands of T-centers, each with 3 nuclear spins and an electron spin. T-centers are coupled to optical cavities for tunability and efficient collection of emitted photons, because T-centers can natively interface with an optical switch network. Modules of T-center computers can be efficiently networked together for horizontal scalability. So here we see now a couple of things. One of them being, okay, we have 3 nuclear spins that are basically these dopants which have been introduced up here, right? So you see the 3 nuclear qubits, the 2 carbons here and the hydrogen here. Then it says an electron spin as well. And then T-centers are coupled optical cavities for tunability and efficient collection of emitted photons. So basically this T-center here is also something that is optically active. So there is an energy transition that can emit a photon or absorb a photon, which makes it interesting for, let's say, moving quantum information around, because if you can convert your quantum information into a photon, you can then send it through a glass fiber and then send it to another qubit, which then absorbs it again and converts it again into some electrical quantum information. That way you can connect different areas of your chips by using entanglement, for example, of 2 qubits that are next to each other and then sending it away as a photon and entangle another chip. You could scale that up pretty quickly. And that's kind of, I think, in my understanding, the promise here. So all-to-all connectivity networked. Here we see the idea, right? So we have 2 different chips that are local to each other, which are connected, but there could also be a third chip which is remote. And it says here, modules are controlled by room temperature control electronics, and photons are routed through room temperature optical switches for cross-module connectivity. At a global scale, photons can pass through fiber networks or satellite links to connect remote computers. And quick comment on that, there is this whole branch of technology around secure quantum communication. I will definitely also make some videos on companies from that space, and there are also videos already on companies from that space. This is the idea of this quantum internet and connecting, using quantum encrypted channels, connecting different data centers with each other. And there are already, in various places of the world, there are already tests running where basically a single photon source is being used, and then you create basically 2 entangled photons, and due to the fact that they are entangled, they carry in some way an information that you cannot eavesdrop in that case. And these are being used in distances over hundreds of kilometers already. Not hundreds, I think. As to my knowledge, there's still this missing piece of the quantum repeater where you can basically repeat quantum information without copying it, because you cannot copy it. There's the non-cloning theorem. But you can already connect quite remote locations with that principle. And now the idea here would be you can create an entanglement between a chip that is sitting here in my data center, I don't know, in whatever, in Cologne, and then you have another one in Düsseldorf in Germany, and you can connect both of them basically using this concept. That's another story if Cologne and Düsseldorf would like to be connected. So, full stack quantum computing and networking. At Photonic, we believe that most performance systems will be performance systems will be the one designed from the ground up with the needs of both computing and networking in mind. We have recruited experts from a wide range of backgrounds and expertise to build a full stack fully integrated system. See our paper, Scalable Fault-Tolerant Quantum Technologies with Silicon Color Centers, for more details about our architecture. And then we see some picture here from the lab. So we see somebody carrying around, I think, what looks like a turbomolecular pump for vacuum setup. We see some cryogenic setups over here with cryostats. There's some optics tables, I think, over here with some additional setups, and a lot of scientists around. And then again, there's the link to the careers page. Furthermore, as per usual, we also see that there's a newsroom here with news and resources. I'm recording this in October 2025. We see the latest news here is from August 2025. But there's also some press releases here from September 2025. And also some news coverage here from October 2025, as well as a blog with September and some white papers and publications, which they are posting here. On top of that, we also see this events tab here, which I guess again covers the different shows and conferences that Photonic is going to visit or has been visiting recently. And let's quickly close today's video with the About Us tab. So connectivity without constraint. Photonic is building one of the first scalable, distributed, fault-tolerant, and unified quantum computing and networking platforms uniquely based on optically linked silicon spin qubits. Photonic's platform offers a native telecom networking interface and the manufacturability of silicon. Photonic has built one of the world's largest teams of quantum silicon experts and curated an incredible array of advisors and collaborators. Multinational partners and investors bring the benefits of global infrastructure, proven platforms, and resources necessary to scale a company led by innovators with deep expertise in delivering distributed technologies. And then we see here the leadership team with Paul Terry as the CEO. We have the Chief Quantum Officer, Stephanie Simmons, and the Chief Financial Officer, Sarah Boatman, as well as many other people here from the team. We also see the science team. On the investor side, we see that Microsoft is an investor here, but we also see that Amadeus Capital Partners, BCI, Inovia, Mubadala Capital, and the National Security Strategic Investment Fund of the British Business Bank is involved in this company. Innovation the world over. So Photonic is headquartered in Canada with global teams in the US, the UK, and throughout Europe. We benefit from the experience and expertise of top talent from around the world. And here we see the talents in the lab. And again, we see the links down here. And with that, I would like to close today's video on Photonic Incorporated. I hope you liked it. If so, please make sure to subscribe to the channel to not miss out on another one, and always make sure to stay hydrated, and see you in the next one. Bye bye.